In this lecture section, we'll look at map projections. After we look at map projections, the next lecture files have to do with data formats and U.S. Census and other data sources and geographic and GIS data files that are used from those sources. A map projection is a way to represent the curved surface of the Earth on a flat surface of a map. The basic problem is that it's impossible to represent a three-dimensional surface in two dimensions without having some kind of distortion. So as a result, there are hundreds of map projections, and each map projection has its own advantages and disadvantages. Each one depends on the scale of the map's purpose, and different projections are good for small areas with a large east-west extent, or areas with a large north-south extent. And this has to do with what kind of distortion can be tolerated for the purposes of the projection. So here are three different classes of map projections. This has to do with the kind of developable surface that the map projection is based on. Features are projected onto one of these three types of developable surface. A planar map is a map projection resulting from the conceptual projection of the Earth onto a tangent or secant plane. A cylindrical projection is where a map projection is projected onto the Earth's surface is projected onto a tangent or secant cylinder, which is then cut lengthwise and laid flat. A conic projection is a map projection where the Earth's surface is projected onto a tangent or secant cone, which is then cut from the apex to the base and laid flat. You can imagine that the basic shape of the developable surface will then affect the shape of the map projection and the kinds of distortion that projection carries with it. First of all, here's the conformal or cylindrical projection in a bit more detail. A cylindrical projection is a type of conformal projection. Conformal projections have parallels and meridians that meet at right angles, and the angles and shapes of small objects are preserved at every point, east-west scale, and the same in the north-south scale. The size, shape, and area of large objects are distorted on a cylindrical or conformal projection, and scale will in effect approach infinity at the poles. This map is really not suited to be used for world maps. Here's an example of a Mercator projection. The purpose of this map originally was to be used for nautical uses. And the basic idea here is that with having straight latitude and longitude lines, a compass could be placed on the map and it could be used for navigation. You can see here that this map distorts distances and areas as one moves away from the equator. That's because the most accurate area on this map projection is at the equator, where there's what's called a scale factor of 1. A scale factor of 1 means that the area on the Earth's surface would represent a true scale of the intended scale of the projection. So for example, if a global map was meant to have a scale of 1 to 20 million, then at the equator, 1 inch would actually represent 20 million inches on the map. Because of distortion as you move away from the equator and the central point of the scale factor, you can expect that by the time you reach 60 degrees north, which would be the latitude that touches the southern tip of Greenland, the scale factor at that point would now be 2, meaning that the area on the map is twice as big as what it is in reality. This map shows Greenland to be larger than South America, when in reality, Greenland is about the size of the Arabian Peninsula. The conic projection is an example of an equivalent projection. An equivalent projection preserves an accurate area, and scale and shape are not preserved. What we mean by that is that this map does a good job of representing areas all over the Earth's surface, but it does it by compromising shape. Notice how the parallels on this map appear to be curved. And that's a result of the equivalency properties of the conic map. As you unroll it, those parallels will inevitably be curved. A compromise projection is neither equivalent nor conformal. In this case, this compromise projection, the Robinson projection, is a good compromise projection that's meant to show the whole world. This is a very common projection to be used for global thematic mapping because it shows the land areas to be roughly approximate to what they are in reality. The meridians curve, they're not too extreme, but there's no way you could use this map for navigation or other purposes related to that. Here's an example of when map projection matters. In your lab, you'll be doing a similar task to this. With small-scale maps, you begin to pick up the reality that distortions can lead to large differences in distance measurements. Small-scale maps occur when you use small-scale maps. You might be comparing shapes, areas, and distances of map features, and the natural appearance of the map is desirable. What we see here, though, is that a map projected using the Mercator projection will show you a distance between New York City and Los Angeles of 3,124 miles approximately, compared to the Albers equal area of 2,455 miles. And in reality, the actual distance is closer to the Albers equal area projection than it is to the Mercator projection. Now, this has happened because of the way that a conformal map maintains those right angles between lines of latitude and longitude. When projection is not important, such as in many kind of large-scale mapping locations where error is negligible, so this map here shows downtown Pittsburgh. The particular projection that's used in this case is most likely a state plane projection for this local area, and that's a fine projection. You're not going to be doing things with it other than using it for reference or to potentially map out features at a large scale. Moving away from the central points on this map, you might pick up some distortions if you were to apply it improperly to a large area, such as a small-scale map of the eastern United States. But that's not a problem for the local case that we're looking at here. This is the end of lecture on map projections. Keep in mind that there's more information in chapter 3 of your textbook, which deals with 2 or 3, which deals with projections in more detail, and we had an earlier lecture on that earlier in the semester.